Welcome, everyone. Well, thank you all for making it tonight. We are super excited to be presenting you the public lecture series hosted by KIPAC, the Kavli Institute for Particle Astrophysics and Cosmology. Well, I know this is our first hybrid event, and for many of you who just joined us online and were actually here to see us in person, it's actually a lot of challenges, but we nailed it. So my name is Singal. I am the Kavli manager of outreach and engagement, and I am one of the co-hosts tonight. So it's really great to see everybody, both in person and online. And now I am going to introduce the other co-host of the night, Dan.
Okay, thank you, Zeman, and thank you everyone for being able to join us tonight. It is wonderful to see those of you both here in the room with us in person and those of you joining us online tonight as we get back to a hybrid mode for our public lectures. So tonight it is our great pleasure to welcome Professor Jack Singal. Jack is an associate professor of physics at the University of Richmond in Virginia. And we're fortunate to have had him joining us here at Stanford for the past couple of months on his sabbatical, where he's been joining us as a visiting scholar. Jack received his PhD in physics from the University of California, Santa Barbara, and then went on to postdoctoral research positions at NASA's Goddard Space Flight Center and here at KIPAC as well. Jack has varied research interests, including applying machine learning strategies to astronomical surveys, exploring how supermassive black holes evolve in our universe, and making new measurements of the mysteriously bright radio emission that we see coming from the background in our sky. But tonight he's going to be telling us about something a little bit different, and that is alien life and UFOs, but from a scientific perspective. But before I hand over to Jack, I'm going to hand back to Zeman, who has a few housekeeping notes for us.
Thank you very much, Dan. Yes, so since this is a hybrid event and the very first one that we host, we are trying our best to engage both the online audience and the in-person audience. So for everyone who's joining us in person today, we will be having a Q&A with Jack, where you will have opportunities to directly ask him questions, and that will be at the end of his presentation. And for all the online participants, hello there, you will see that on your right-hand side of the YouTube page, there's a live chat box. We welcome all kinds of questions and also encourage you to engage in discussions. So to manage the large group we have online, we actually have 3 chat moderators who are all subject matter experts from Stanford, and now I will have them to introduce themselves. So first we have Renee.
Hi everyone, my name is Brene Hadnot. I am the data curator and storyteller at KIPAC, and my background is in planetary science, and I'm super excited to be here. Thanks.
And next we have Bill.
Hi, everyone. I'm Bill Robertson. I'm an undergraduate here at Stanford, and currently I'm researching binary star systems and what they can teach us about exoplanets, specifically directly imaged exoplanets.
And finally, we have Sadav. Sadav, you want to come here?
Hi, I'm Sadav. I'm a first year graduate student here at KIPAC, and I'm doing research in
Great, thank you all. So for this event, especially if you're participating online, most of the questions will be handled by the chat moderators as they come in. And for the remaining questions, Jack will be answering them during the Q&A session. So Jack, of course, will also be available for conversations after the event if you're here in person. And if you are attending, we suggest that you actually put your cell phone in silent mode. As you can see, you know, our mic are picking up sounds very sensitively. Right, so without further ado, I'll hand it to you, Jack.
Thank you. Are there other beings out there? Do they have minds like we do? This is an old question. In fact, the earliest recorded example we have of people discussing the existence of aliens is not from science fiction. It's not from some Renaissance polymath. It goes all the way back to Greco-Roman times. The philosopher Epicurus, he wrote there's an unlimited number of worlds, and some are similar to this one and some are dissimilar. One of his followers then later said, in other realms, there are still other worlds, still other breeds of men. By the Middle Ages, this was a topic of theological dispute. There was a priest named Giordano Bruno who said, I can imagine an infinite number of worlds like the earth with a Garden of Eden on each one. And of course, a Garden of Eden is where people come from in his mind. By the 20th century, this became widespread in the culture to imagine what other worlds were like, to imagine the beings that were there, and even to imagine that they were visiting us in strange spaceships. But all people could do was speculate. Now, 2 decades into the 21st century, we can do more than just speculate. We finally know more than we used to. We do have to give an honorable mention, though, to one very important thing we did learn in the 20th century, which is that there is no other intelligent life in our solar system, or at least no civilizations out there. We've just seen all these planets and moons up close, and there are no cities there. If there is life somewhere else in the solar system, it's microscopic. And so, if intelligent life exists out there, it must be on or around a planet that's outside of our solar system. Which brings us to a scientific or mathematical formulation of the question. Is there intelligent life out there? Now, people frequently say, do not have an equation in a public talk. But I'm looking out and I'm seeing a sophisticated audience, mostly. And I think you can handle it. It's just a bunch of things multiplied together. Just want to mention, I'm seeing the camera off. We have the Drake equation, and it's a way to express the number of technologically advanced civilizations that we have in our galaxy at this time. And as I said, it's a bunch of things multiplied together so we can handle that. And here is that number, the number of alien civilizations in our galaxy, the number of civilizations in our galaxy. And here's the things we will multiply together. This R star is the rate of formation of stars. Now, really, we want the rate of formation of stars several billion years ago so that this life would have time to evolve. This F sub p is the fraction of stars that have planets. We think that life can't exist on a star, it's too hot, but we need some of that warmth. So a planet is the place to be. Then we have this N sub e. That's the average number of planets or moons per planetary system that are suitable for intelligent life. What that means, we'll see. Then we have this F sub L. That's the fraction of times when we have a habitable planet that life actually arises. Then we have this F sub I. That's the fraction of life that evolves into intelligent species. Then we have this F sub E. That's the fraction of intelligent species that end up developing advanced technology. And then finally, we have this T. This is the average length of time that a civilization spends with advanced technology. Now, for us, we can imagine it's been something like 100 years, if we want to date it from the beginning of wireless communication, or a little less if we want to date it from the beginning of digital processing. But whatever it is, about 100 years. And we don't know if these things go and go and go, or if they stop, cause civilizations fall, or people just decide to go back to farming or hunting or whatever. Now, 20 years ago, if I was giving this talk, we would have speculation across the board for all of these numbers. But now we have answers for the astronomical questions that are in here. And the reason is because of our revolution in understanding of exoplanets. Exoplanets is short for extrasolar planets. That's the planets that are outside of our solar system. As we said, intelligent life, other intelligent life will have to be outside of our solar system. And it's remarkable to step back to think that as recently as 1993, the total number of known exoplanets was 0. We did not have a definite answer to the question, are there any other planets in the universe other than the ones in our solar system? Even 10 years ago, it was less than 100. But now it's over 5,000 and rapidly increasing. Here's a visualization of that revolution. This is the total number of known exoplanets through the years. And you can see that really big takeoff there after 2010. So let's discuss how we know that these planets are out there. Well, the simplest thing you might think would just be to see them through a telescope. But actually, this is not very simple because stars are bright and planets are dim. And from our perspective, these things are very close together out there. But if you insist on an image that you might be able to collect with a telescope, here's one. That is a planet definitely around that star. That planet, though, is not typical. It's enormous. And so, being a very big planet, it's reflecting a lot of light, and we are seeing it directly. There are some techniques to try to block out the star's light in a telescope image, and then see dimmer things around it. So here's a star with several planets. But this is not a common way to find. Another way is to see that the stars are wobbling because the planets are pulling on them. And to understand this, we want to remind ourselves of something we've all experienced. Our horn or a train whistle or ambulance siren going past, it goes from high pitch to low pitch. Now, why does that happen as that object is moving? It happens because sound is a wave, and as an object is traveling toward us, it's getting closer each time it emits, let's say, a peak of that wave. And so in front of the object, the peaks of the waves are piled up together. Behind the object, the opposite thing is happening. As that horn moves away from us, it's farther and farther each time it emits a peak of the wave that starts coming toward us. So the peaks are pulled apart behind the object. So when it's coming toward us, peaks are stacked up. When it moves away, peaks are pulled apart. When it comes to sound, close together peaks is higher pitch. Farther apart, peaks is lower pitch. And so that's what we hear. Well, light is also a wave. And so we can look at a star and see this. Here we will see a star with a planet going around it. Now, we don't see that planet. We don't even see the star move. But the star's moving a little bit because of the planet's gravitational pull. Now, watch the star come toward us and then away from us. Toward us and then away from us, over and over. Because light is a wave, when it's coming toward us, it's shifted to higher frequency. When it's moving away from us, it's shifted to lower frequency. We see the position of these absorption and emission lines shift in frequency. Up, down in a regular pattern. That means even though we don't see this planet, even though we don't see this star, we know it's moving like that, and we know the planet's pulling on the star. But the most important way that we see the planets is the transit method. This is where we have the brief, slight dimming of a star as a planet passes in front. And here's where I have a demonstration. We'll need the camera. Okay. All right, so here I have a star, and you're way in the distance from this star. If a planet is going around this star, then at some point it could block out a portion of the light from that star. Here's an example of our own planet Venus in front of the sun. And you can see there it's blocking out about 1% of the sun's light. Now that might not seem like a lot, but if we could see 1% of a star's light being blocked, we would know a planet's there. So we want to see a distant star dim just a little bit. It's a tough measurement, but we had the Kepler satellite, which had one job, which was to go up and stare at that patch of stars there and see if any of them would dim. And it saw stuff like this. Here's some data from staring at a star. The top panel there shows the light, and you can see these distinct dips as the planet passes in front of the star from our perspective. Now, if you see the numbers there, that's less than 1% of a dip. But it's still there. And if it's happening over and over, that means the planet is going around the star, passing in front. Now, there's on the second panel there, is that blown up, and you can see there's even more structure there. You can see that before the dip, it looks like it's getting a little bit dimmer. After the dip, it gets brighter. And then there's even a little bit. What's going on there? Well, let's visualize this. Here's the star, here's the planet. As we come around from behind the planet, you can see that, from behind the star, you can see that the planet would be almost entirely light from your perspective, because it's reflecting the light of the star. But it comes around here, and the light side of the planet is now facing the star, not you. And then it comes around, and more of the light side of the planet is facing you. And then eventually the planet goes behind the star, and we lose the light from the planet. So this structure here tells us a lot. We see how much light the planet is reflecting when we lose it behind the star. And we see this more and less of the bright side of the planet facing us. And so we can get a lot of information about the planets. From the timing of the dips, we get the period of the orbit. How long does it take to go once around? There's a formula from introductory physics where we can get the distance of the planet once we have the period and the mass of the star. With the distance and the amount of light dimming when it passes in front of the star and when it reflects the light, we can get an estimate of the planet's size. With the size and the amount of light the planet appears to reflect, we can even get a sense of the composition. With the composition and the planet's size, we can get an estimate of the mass even. And maybe we can even combine this with the wobbling star to get another estimate of mass and distance. And so put it all together, and we have 5,000 confirmed exoplanets so far. There are a lot of planets out there. In fact, if we come back to thinking about the transit, if the planet was orbiting like this around the star, we would never see any change, because it's never passing in front of the star from our perspective. And so we're missing a lot of the planets even. We're seeing that they come in all different sizes and distances from their star. And there are many multiple planet systems. We have 2, 3, 4, 5, 6, 7, and even an example of 8 planets around the star. 8 is a very intriguing number. Why? Because it's the number of planets that we have. Here's a way to visualize the planets. We can plot out their orbital period, which is also standing in for the distance from their star, and their size. Now, as you can see, because of these methods, we are biased towards seeing the biggest planets because they have the most effect, whatever. And oftentimes the ones that are closest to their star, in part because we need to be able to see these dips in the time we've been looking. Something like Neptune has a really long orbital period, way longer than the 4 years, for example, that Kepler was looking. So we are missing a lot of them. But you can see here that in terms of the orbital period and the size, we do have ones that are similar to Earth. Our orbital period is 365 years. So we are seeing planets that can support life. We're seeing the existence of planets that can support life. Now, people think of that in terms of what's called the habitable zone. For a given star, too close would mean too hot. Too far would be too cold. So there would be a distance of an orbit that would give the right temperatures to, for example, support liquid water. Water is a good medium to have a lot of complex stuff going on, including life. And we do know of many planets in the habitable zone around their star. Here are ones that are so-called Earth analogs. So these are planets that are in the habitable zone and roughly similar in size to Earth. And they're even given something that's called an Earth similarity index there. And that takes into account several factors that make it more or less like Earth, like the size, orbital distance, and so on. This is, of course, artist's conception of all these planets. We don't have any idea what they actually look like. But you can see there's many promising candidates to be like Earth. Even the closest other star to us, it's called Proxima Centauri, and it has planets. It has at least 2 planets. And one of them is in its habitable zone. That planet is called Proxima Centauri b. This planet is slightly larger than Earth, and it does orbit very close to this star, because this star is much dimmer than the sun. But nevertheless, it's in the habitable zone. And so the closest possible place outside of our solar system could potentially support life. Here's another honorable mention. Kepler 452b has been referred to as an Earth cousin. Its star is very similar to our sun. Its orbital distance is about the same as Earth. It has a density consistent with the rocky surface. It's about 2 times as big as Earth, but that's probably it. And so these results show that, from what we can see, a significant fraction of stars do have planets, and we're missing a lot of them. And so take all of these planets and then say there's 100 billion stars in the Milky Way galaxy. And if we want to go outside the galaxy, 100 billion galaxies or more in the observable universe, there are a lot of planets out there. There are a lot of potential places for beings to live. And now that we know all of this, we can put some numbers back in the Drake equation that we saw at the start. So let's do that. Let's put some numbers in. Well, our star, the rate of formation of stars that we know from astronomy and astrophysics, let's call it 1 per year. Now, the fraction of stars that have planets. I think we can say that for purposes of estimating here, it's all of them. We're seeing enough stars with planets and we know we're missing a lot of them. Now, the average number of planets or moons of a planet per system that could support intelligent life, that is, let's say in the habitable zone. Well, based on the fact that we're seeing so many multiple planet systems, let's call that one per system. Now we have the fraction of habitable planets where life arises. And now we're back to speculating. Here we don't know because this is not an astronomical question. Really, this is a biological question. And so now I will have to make a guess. So you might say half, but I will be a little bit bold and go with half. Let's say half the time, given the right conditions in a habitable zone, we have life arise. The fraction of life that evolves into intelligent species. Here we have another guess from biology. We might think it's pretty rare, right? Because it took us a long time to get here on Earth, right? 2 billion years approximately of life before we got here. But I think that if us primates hadn't done it, there were other promising things out there on Earth. Dolphins and whales are very smart. People say that crows never forget a face. Even supposedly octopus pull pranks on their keepers. And so I would give this maybe a half. If it hadn't have been us, it could have been somebody else, even here on Earth. Now, fraction of intelligent species that develop advanced technology, well, that's also very difficult to know right now. It took human beings, depending on how you count, 1 million years, several 100,000 years. I'll call that also half, given the right conditions. And then the average length of time in the advanced technological stage, well, like we said, we're approaching 100 years. I'll put what I think is a conservative number in here for 1,000 years. Because it seems like probably if you make it 1,000 years, you might be good to go for another 1,000 or 10,000. But just to get a number in here, let's call it 1,000 years. And then we can multiply all of these numbers together. And this is 125. 125 advanced civilizations in our galaxy for these possibly conservative guesses. But notice the unknowns are from biology and sociology. We've answered the astronomical questions to go in. So, potentially 100, or even if we were too generous there, cut that down by a factor of 10, 10, 5, potentially other civilizations in our galaxy. Well, some of you may have heard the search for extraterrestrial intelligence. This is in progress, looking for communications in intentional communication signals or intentional radar signals from another civilization in radio waves. They say that they would be able to detect a civilization sending out intentional communication if it was from approximately that portion or that fraction of the galaxy around us within a couple of decades. Now, with the numbers that we thought about there, let's say 125, there would be several within that region of the galaxy. And if they're intentionally communicating, we should know about them. We should mention that we did this once. We sent out an intentional communication towards a globular cluster of stars once. We've also been doing some planetary radar. So it's also possible that in roughly that region of the galaxy, they would be aware of our presence. So under the assumptions that we put in the Drake equation, we do have a distinct possibility of detecting an intentional communication from the civilization in a few decades. Now, there's an interesting thought puzzle, which is called the Fermi paradox. Enrico Fermi was a prominent physicist in the 20th century who worked on a lot of things. And one thing he thought about was that if there's even one other civilization in the galaxy that has had a long technological life, they should be here by now. And the thinking there goes, well, it would take millions of years to colonize the galaxy, to build a bunch of spaceships and go out to a different planet and seed that planet and build it up and build spaceships to go out to some other planet. This would take millions, tens of millions, hundreds of millions of years, even if you want. But there are stars that are billions of years older than the sun. So if there were life on those planets, they've had plenty of time to evolve to a civilization. And so where are they? Where are the older civilizations, if not here? Well, some possible resolutions of the Fermi paradox or apparent paradox that people have come up with. Maybe all civilizations do self-destruct or go quiet. Maybe we really are the first and maybe only advanced civilization. Maybe the numbers we estimated in the Drake equation were way off. Maybe other civilizations are aware of us and leaving us alone, just watching. Or something that I have thought. But this does bring us to an intriguing observation or set of observations that have been made recently. We have an object that is on a seemingly strange trajectory through the solar system. It's called Oumuamua. And it appears to be going around, slingshotting around the sun in a way that would not be just due to the sun's gravitational pull. It appears that it has some other source of acceleration. And furthermore, it's undergoing big changes in the amount of light it reflects from the sun towards us. So if we imagine it shaped like a cigar or a remote control, and it's tumbling through space, you can see that sometimes the big face of the remote control will be facing us, and sometimes the little face of the remote control will be facing us. So it gets brighter and dimmer. Now, we don't actually see what it looks like. It's just a pixel getting brighter and dimmer. But it undergoes big changes in the amount of light it reflects towards us, which suggests a possible strange shape, like a remote control or a cigar or something like this. And so the strange trajectory combined with the strange shape has led a number of people to speculate that Oumuamua might be something sent from another civilization. The chair of the Harvard Astronomy Department, Autumn Loeb, has written a book saying that we should at least consider seriously this possibility. Well, that brings us to the topic of UFOs. And when it comes to UFOs, because of everything we've seen from the Drake equation, it's a universe of fascinating, crazy things. I encourage people to approach the question of UFOs from a perspective of what I would call open-minded skepticism. We start from that it is a big leap from saying there is likely life out there in the galaxy based on the assumptions we put in the Drake equation. And it may even know about our civilization. There are several within that region of the galaxy circle that we show. It is a big leap from that to they are visiting us by flying around our sky in strange vehicles without just stopping and saying, hi, we're here. Of course, there are then strange allegations of them being in secret collusion with human governments, abducting people for strange medical experiments, and looking a lot like cartoons. The question of UFOs has been a cultural obsession for about 80 years now. The UFO era began in World War II, when pilots would see strange lights and shapes whizzing across the sky. They called them Foo Fighters at that time. There was, of course, the famous supposed crash of a spaceship in Roswell, New Mexico. There were a number of incidents where many people, saw strange lights or shapes in the sky moving around, took photos, some more believable than others. But this all reached a head last summer, when the Pentagon released declassified videos that showed strange shapes whizzing around the sky. And because it's the Pentagon, it's declassified, we can't immediately dismiss it as just some random person's photos. But if we look at this carefully, let's start by seeing what I would consider a typical news report about this.
In night vision video from a Navy destroyer, a mysterious flying triangle above the deck of the ship. The Pentagon confirming the images obtained by documentary filmmaker Jeremy Corbell were taken by Navy personnel, expected to be a part of a report on unidentified aerial phenomenon to be presented to Congress this summer. Already online, some skeptics say the images are caused by cameras trying to focus, but some of the objects go beyond just flying in the sky. One shows a spherical object dipping into the ocean, similar to an incident in Puerto Rico, where an object was tracked buzzing an airport, then flying into the water, popping back out before appearing to split into two and disappearing. Over the last several weeks, some of the nation's top former intelligence officials have been raising eyebrows.
It's rotated.
Former CIA Director R. James Woolsey said he knew of a case where a plane was paused in midair.
All right, well, when we see a news report like that, I encourage us to consider it with several stages of appropriate skepticism. So the first is that any video on any topic that you see on social media or websites or television shows that depend on clicks or ad revenue should be automatically assumed to have been deceptively edited in some way. It's how you get more clicks and more eyeballs. For example, crucial context before or after the event has been cut. The video could be sped up or slowed down to make these motions seem even more bizarre. Maybe sped up then slowed down. These videos have clearly been cropped to remove things on the side, which could provide context for size. How do I know if I'm looking at a frame that's a huge part of the sky or a tiny part of the sky? Next, I think we really need to consider if we're seeing mundane objects like kites or drones or even frisbees. Some of those images in those videos, I couldn't tell that it's not that. These videos are often blurry, and as we've seen, missing objects for size reference, speed reference. The motions are really difficult to assess. They say it's whizzing across the sky and darting from here to there, but I can't really tell that from the videos they're showing. It might be, but I can't tell it from those videos. Well, even if we can think that we can account for deceptive edits and the lack of context, and we're pretty sure we're not seeing any sort of mundane object, we do have to ask why we jump immediately to alien vehicles coming to look at us without stopping to say hi, rather than atmospheric effects. Our atmosphere is, after all, an extremely strange place. Just think about a tornado. It can pick up and throw a car or a cow. We have hailstones, big as boulders. This is a real picture on the left there of a sunset in polar regions where the refraction causes there to really look like there are 3 suns. We have double and triple rainbows. Just think about a rainbow itself, a single rainbow. That's an incredible optical effect that our atmosphere is giving us. And so if it can give us a rainbow with all those colors, could it give us a dark blob moving a little bit? Probably could. And so we should remember that our atmosphere is a crazy, strange place also. And not immediately jump to thinking that we must be seeing something from outside. And so I have now, to wrap this up, some takeaways. In fact, in the past 15 years now, here in the 21st century, we've learned a lot about the astronomical numbers that are needed to assess whether intelligent life is out there. Remember the astronomical numbers. We found that planets are quite common in the galaxy. There's an enormous variety of solar system configurations out there. 2, 3, 4, 5, 6, 7, 8, probably more planets. All kinds of distances from their star. And we know there are many planets in the habitable zone around their star, and many that are Earth-like in terms of habitable, size, and other considerations that we might have. So our astronomical considerations point to there probably being other technologically advanced civilizations in the galaxy, maybe a significant number. Although remember, the unknowns are from biology and sociology, so we had to make some guesses. It is possible that alien civilizations would visit Earth, especially in light of the Fermi paradox, but we should be generally skeptical of reports and videos of UFOs of the type that we see, because there are ubiquitous deceptive edits for clickbait and ratings. There are mundane objects that I find it difficult to rule out in those videos. And there are crazy atmospheric phenomena. That brings me to the end of this talk. Thank you for your interest.
Very much for that amazing talk. That really was fascinating. So at this point, I would like to invite questions from those of you in the room and also from those of you joining online. I have my iPad here with any questions that you send in via the YouTube chat, I can see. So let's get started. Does anyone have any questions for Jack? Yes, at the front.
So speaking of the comet that was seeming like it was accelerated by something else, do you believe that that could have been from some intelligent life form?
Yeah, I was a little bit afraid of that question. The question was about Oumuamua, the object that has a seemingly strange trajectory and maybe a strange shape. And the question was, do I think it could be an object from another civilization? Yeah, and I appreciate the way you phrased that, because yes, I think it could. It's an intriguing possibility.
There would be ways to prove that?
But unfortunately, probably not. It's slingshotting around the sun and on its way.
I see. Thank you.
So it seems as if this talk has promoted a healthy discussion actually amongst our online attendees. And one of the questions that came out from that is what exactly qualifies as intelligent life? And would we be able to detect non-intelligent life? That's
a great question. I think I would like to define it as capable of developing an advanced technological civilization. So I would like to, for these purposes, define intelligent life that way. And so we know that we are capable of developing an advanced technological civilization because we did. Whereas a cat's probably for a number of reasons, right? Even though they seem to have some level of intelligence. So I think for this, I would define it that way. And then as far as detecting non-intelligent life, so there are ideas and proposals to be able to look in the direction of stars and do what's called a spectrum, where you split the light out into a bunch of little different frequencies to see specific substances that are emitting light or absorbing light at those frequencies. And so it might be possible, for example, to detect the presence of oxygen and carbon dioxide simultaneously in the direction of a star. And then that could be a potential indicator that non-intelligent life or any life is there. And there would be other organic compounds that could be detected that way. So that's one method.
Another related note, another question we received is if you don't insist on intelligent life, does the number n in the Drake equation become reasonably large?
Yes, I think it would. I think if you don't insist on intelligent life, then some of those fractions that were 0.5 or lower would be 1, and that the Drake equation number then for just overall life would be quite a bit larger, an order of magnitude or so, or more.
Okay, great. Yes, in the middle.
Yeah, so when you were optimistic with the Drake equation earlier, you gave pretty optimistic, I think, estimates for many of the terms. On the flip side, do you also have like a pessimistic total estimate, a reasonable worst case that you think is also not highly likely?
Yeah. So the question was that there was a notion that the numbers that we put in the Drake equation there for the biological and sociological terms were optimistic. And let me just say that could be the case for things like the fraction of habitable planets where life arises, and the fraction that go on to intelligent species. I think I may have been pessimistic on the average length of time, right? Because longer-lived civilizations would presumably be very long-lived in the millions of years, so that pushed that average up. So what about a pessimistic assumption then was kind of the end of that. So if we took 2 of those 0.5s to 0.1, we would cut that by a factor of 25, and it would still give 2 or 3. So to me, that would, now of course the most pessimistic you can get is just us. But even if we cut those down to 0.1s, we'd get 2 or 3, and sorry, even up to 5 in the galaxy.
Yes, there's a question at the back.
Thank you. The lecture was really interesting. You mentioned that looking at the star from a specific angle, it enables you to see the planets that are orbiting it, right? So with looking at it from a different angle would enable you maybe to see other planets that you couldn't see from that angle.
So the question.
Can you explain how many directions are we trying to look and find the planets?
Yeah, I'll if you don't mind, I'll use the props again. So the question was that since we said that from our perspective, if the planet comes around here, it will block the light of the star. But if it's orbiting like this, it will not block the light of the star from our perspective. And so could we look at the star from a different angle in order to see the light being blocked if the planet's orbiting this way? Well, we'd have to go way over to some very far part of the galaxy in order to get a different angle on that star, right? We wouldn't be able to look from over there. We'd have to look from over there. And so we can't get anywhere near that far to get a different angle on the star. Yeah. Couldn't do it. Good thought.
One question that's come up a couple of times is you make a very optimistic assumption in your Drake equation that every star has a planet around it, whereas some other people might say maybe only half of stars have a planet around them. So I wonder if you could say a couple of words on what that assumption is based on and what the latest research and the latest thinking is on that question.
So that was, I'll definitely own up to that was my own estimate there. And I think I'm basing that on, again, the frequency with which people are detecting planets around all of these stars, and then the ones that we know we would be missing. the ones where the planets are orbiting in a different plane where it doesn't come between the star and us. But planets with longer orbital periods, and anybody's been doing this. And so that's the optimistic case that I'm using there. But again, even if we cut that down to 0.5, it's only cutting the number of civilizations in half.
Sure. And there's a question at the front here.
Oh, I didn't forget my question. It was, why haven't aliens talked to us yet?
So the question is, why haven't aliens talked to us yet?
Is it because their mode of communication might be different, or is it because that it's physically impossible for them to communicate with us?
So I think the best answer is we've only been listening for a relatively short amount of time. Right, we've only been doing any wireless communication technologies for about 130 years, right? And if you take the speed of light times that amount of time, it doesn't cover a large fraction of the galaxy. And also, they could be, they could have sent a communication signal or a planetary radar signal that was just at some point when nobody was listening in that frequency. And so I think the short answer is we just haven't been listening long enough to say that whether or not they're communicating.
Yes, right at the back.
Thank you for the excellent lecture. I just wanted to clarify one point. So when the estimate that there's a dozen or so, or a quarter of a dozen civilizations, you mean right now, right? Because the last number is the length. So at any one time.
Correct. Yes. Currently, thank you. Good question. So the question was, is that the Drake equation estimate is for the number of civilizations that are currently active, and that's. But it's sort of time invariant.
I also want to take a stab at answering the Fermi paradox, but maybe considering something that's missing. Because as far as we know, the physics we understand is the physics that is out there in the universe. And so I wanted to get your comment on whether, if you live for a very long time as a civilization, you realize it's energetically impossible to travel in their star system. You can't muster the energy to send signals continuously. Do you think it's possible that the Fermi paradox is a measure of physics being kind of what we see, and after a while you just realize there's no point in trying?
Yeah, so that's a very good point. The comment was that, I'll just quickly summarize it, that the possible resolution to the Fermi paradox is that it's actually not that straightforward to just go out and colonize another planet and then colonize another planet and so on, that there's potentially kind of fundamental energetic considerations and limits there that we haven't experienced yet because we haven't tried to do it. Is that good? Yeah. It's possible, although it seems like with the exponential pace of technology that's something that if I had to guess, I would say is not limiting, but definitely could.
And the question at the front.
So the Drake equation uses the rate of star formation,
yeah,
and then multiplies that by the number of habitable planets. Is there a reason that you don't just use like the number? Why the rate of star formation instead of like number of stars in the Milky Way or something? Why are we?
Well, I think it's to make the units work out because we had a quantity with dimensions of time at the end there, right?
Oh.
Yeah, sorry. Then the question. Sorry, I forgot to repeat the question. The question was, why do we use the rate of star formation in the Drake equation as the first factor in there, rather than say just a number? And I think it's in order to make the units work out, because in the end we're multiplying it by something that has dimensions of time, the average length of a technological civilization. Good question. Thank you.
Yeah, the interesting question we had online actually. Do you know if any indigenous civilizations ever pondered the prospect of alien life or life beyond that planet?
Yeah, that's a great question. I personally don't particularly know, but yeah, if I had to guess, I'd say that they probably did if they were sitting around thinking about it.
And yes.
I just want to ask the speaker a question. So probably probability of you, if you were an intelligent being beyond human levels, current human levels, that you would contact us in like a lower intelligence level.
So the question was, should we think it's, let me phrase it this way, should we think it's likely that a very advanced civilization would want to contact less advanced civilizations?
Yeah, would they see like from afar, hey man, these guys are kind of like kind of weak and they don't have the technology we do.
Right. Yeah, I mean it's very, I'd say I would say it's very difficult to generalize, right? Because different civilizations may have different cultures and different ideas in that regard, right? But one thing to think about is that if they get a snapshot of how we were in 1965 or something, or whenever that intentional signal was sent out, right? That in the time it takes to get there, they might reasonably conclude that we've come along. In the time the signal takes to get there, which could be decades or longer, they might reasonably conclude we've come along with in our technology since then, which we have.
Hopefully they can help us advance too.
Sure. So let me just wrap up. We've got time for just one more question. And I'm going to ask you what you think, Jack. And I'm going to ask you to make a prediction here. So do you think that we'll discover alien life within the next 50 years or so?
Yes.
Well, you heard it here first, folks. Well, thank you again, Jack. Let's thank Jack again. Before we wrap up, we get back over to Zina, who is going to tell us about how we can keep up with events going on at KIPAC. So over to you, Zina.
Well, thank you, Dan, and hello, everyone. It's me again, and now you should be able to see me sharing my screen. So here are some channels that you can actually follow us in different ways if you want to keep coming back to more KIPAC lectures or outreach events in the future. So for the public lecture series, you can see that here is our website, and you can simply just type in kipac.stanford.edu /discover. And here are actually all this is the current lecture and all the past lectures. And we have actually scheduled our next event to be on April 5th. And that is going to be First Stars. So it's, we're hoping to make it a hybrid event again. And if you're interested, come back. Some other social media channels that you could also follow us include Facebook, if you have Facebook. And whenever we have an event, we will definitely post it here. And sometimes we also post interesting things that includes, KIPAC news and interview pieces. And of course, how can we miss having a Twitter account? So we are at KIPAC1, that's our Twitter handle if you want to follow us. And finally, if you're, well, I would assume that all of you have registered on Eventbrite. So here is actually our Eventbrite page, and you can see right here that the registration for the next event, First Stars, that is on April 5th, it's already open. So if you want to register, simply just click register, and it's a very quick process. And finally, I would like to thank everybody, either you're joining us online or in person to have this event. So I would like to just bring everybody back to the screen. Let me stop sharing so we could just say an in-person goodbye. Yes, well, thank you all very much. That we are very grateful you are spending this evening here with us. And we are going to send out a survey to collect all your feedback. How did you like it? What did you like? What do you want to hear and to learn more about in the future? This is our first hybrid event, and I know, as you can probably see, we're still struggling a little bit, but we are doing our best. So we would definitely want to hear from you and try to become better in the future. And the email will also include a link to sign up for our email list if you're interested to be notified of our future events. So with that, any final thoughts, Dan?
Just to say thank you everyone for coming. Thank you for joining us online and in person. And thank you, Jack, for that wonderful talk.
Thank you very much.
All right. Thank you, everyone. Have a good night.